In today's video, we're going to look at the two equations you need to know about elasticity. The first, F equals KE, links the force that you apply to an object to how much it extends by when you apply that force, with K being the spring constant, which is specific to each object and is a measure of how firm or elastic the object is. A lower spring constant means that the object is more elastic, and so easier to stretch, while a higher spring constant means that the object is more stiff, and so harder to stretch. The other equation is that elastic potential energy equals 1/2 Ke squared, where K and E are the spring constant and extension again. And importantly, it's only the extension that's being squared, not the whole thing. You can think of elastic potential energy as the energy transferred to an object as it's stretched. So if you used 100 joules of energy to stretch a spring, then the 100 joules would be transferred to the spring's elastic potential energy store. And then when you let it go and it springs back, it will transfer that 100 joules back out to a different form, like kinetic energy. To see how these equations work, let's try a couple of examples. Imagine this spring has a natural length of 0.6 meters. But when we apply a force of 14 newtons, it stretches to 0.8 meters. What's the spring constant of the spring? Well, first we need to figure out what's going on. As the spring has stretched from 0.6 to 0.8 meters, we can find this extension by subtracting 0.6 from 0.8, which gives us 0.2 meters. So we now know the force and the extension, and we want to find the spring constant. If we look at our two equations, we can see that we would have to use F equals Ke, and then rearrange it to get F over E equals K, which if we plug in 14 divided by 0.2, gives us 70 newtons per meter as our spring constant. Now, using the same scenario, what would the elastic potential energy of the spring now be? This time, we're going to have to use the other equation. So, elastic potential energy equals 1/2 Ke squared. And it's a bit simpler, because we've already worked out the spring constant and the extension. So all we have to do is plug the values into the equation. So we get 1/2, or 0.5, times 70, times 0.2 squared, which gives us 1.4 joules. The last thing we want to point out is that if you have a graph of force against extension, like this one, then as long as we only look at the straight part of the line, the gradient of the line will be the spring constant, and the area under the curve is equal to the energy transferred to the spring, so the elastic potential energy. And just to recap, remember that this point here is known as the elastic limit, or the limit of proportionality, and it's when the object stops obeying Hooke's law.